Alright, thanks for watching, and today I would like to talk to you about the most powerful result in linear algebra and one of the coolest proofs in linear algebra, the Cayley-Hamilton Theorem. What does that say? So, just for an example, consider the matrix 1, minus 1, 2, 4. Then it turns out its characteristic polynomial, let's write it like this, a minus lambda I. If you take the determinant, if you calculate it, it would be lambda squared minus 5 lambda plus 6. And particularly the eigenvalues are 2 and 3. And to find the eigenvalues, you set that equal to 0. But this is not the point of today. The cool thing is, suppose you take this characteristic polynomial and you plug in a for it. So suppose you calculate a squared minus 5a plus 6. Well, 6 times the identity. It turns out if you do that, you get the 0 matrix, which is 0, 0, 0, 0. And in fact, this is always true, and that's what's called the Cayley-Hamilton Theorem, and this is what I would like to talk about today. And it has a bunch of lemmas, so it might be a long video, my apologies. But first of all, it has to do with what's called invariant subspaces. So suppose you have a linear transformation from V to V, so T, and a subspace, let's call it W. Let me use some colors. Then there's some special subspaces called T-invariant subspaces, and this means W is T-invariant if whenever you start with a vector in W, T of x is still in W. If x in W implies T of x in W. Think of W as your home. In the beginning of the day, you're at home, and then you're walking back home at the end of the day, hopefully. So home is a T-invariant subspace. And why is that useful? Because if whenever x is in W, T of x is in W, we can define a mini linear transformation called the restriction, which is just T, but on the smaller subspace. So then T restricted to W goes from W to W is defined by the same formula. T restricted W of x is just T of x. So again, this is like a smaller linear transformation. It's the same formula as T, but on this smaller subspace, and it's still a linear operator. So that works. And the cool thing is, the characteristic polynomial of T and the characteristic polynomial of its restriction are related, namely as follows. So lemma 1, the characteristic polynomial of T restricted to W actually divides the characteristic polynomial of T. So let this be 1G, and let this be F. Then G as a polynomial divides the polynomial of T. So in some sense, it's a smaller version of T. And here's just the idea of the proof. So let's calculate the matrix of T, and the idea is, let's start with the basis for W and then extend it to a basis of V, and let's call that basis beta, and let's calculate the matrix of T with respect to beta. And how do you do that? Well, for every element in W, calculate T of that element. So for every basis vector in W, calculate T of that basis. Then what you get is a bunch of elements, but also a bunch of zeros. Why is that? Because whenever you start with a vector in W and apply T to it, you get something in W. So you express it in terms of W, and all the other vectors become 0. And continuing, what you get then is a matrix which bunch of zeros. Here it's whatever, and then the rest are also some matrices. So let's call those A, B, and C. A, B, and C. And the cool thing is this matrix A is just the matrix of the restriction. Because what is T restricted to W is just you apply T to the vectors in W and you express them in terms of W. So that's really the matrix of T restricted to W. And then what is the characteristic polynomial? So f of lambda, it's determinant of that matrix minus lambda I, which here becomes determinant of A minus lambda I, B, C minus lambda I, 0. And the nice thing is about determinants, even for block matrices, is the determinant of this is this times this. So that's the determinant of A minus lambda I times the determinant of C minus lambda I. But by definition, this is the characteristic polynomial of T restricted to W. Because remember, this is the matrix of T restricted to W. So we get G of lambda times some other polynomial. That's what we want. The characteristic polynomial of T equals to the characteristic polynomial of G of T restricted to W times some other polynomial. And that's the definition of divides. It says the original polynomial is a multiple of the polynomial that we want. All right, so this is, again, very heuristically, I showed that. Of course, you would have to fill in the details, but this is heuristically why it's true. Then, we need another lemma. Because you see, once we have something invariant, a T-invariant space, let's say W, what this means is that if you start with a vector v and apply t to it, you get another vector tv. If you apply t again, you get a vector t squared of v. And then just continue like that. And in fact, invariant subspaces, they're very important in dynamical systems. Think like billiards. You start with the billiard ball, you push it, it gets somewhere else in your space, and you push it again, and you push it again. And you want to ask yourselves, well, what happens to this orbit? And in fact, so lemma 2. Let W be this T-cyclic subspace generated by V, by some vector in V. So in other words, so W is V, T of V, T squared of V, T cubed of V, etc., etc. In other words, consider, the span of this. So consider the span of a vector, then its orbit, then its orbit, then its orbit. So you can show that it's indeed T invariant. And in fact, it's the smallest T invariant subspace containing a vector. So it would be V, and then T of V, and T squared of V, etc., etc. If you take the span of that, you get your T-cyclic subspace. And one can show it's finite dimensional, and in fact, suppose K is a dimension of V, W. I mean, of course, if V is finite dimensional, this is finite dimensional because it's a subset of V. So that makes sense. So let K be the dimension of V. Then the cool thing is there's a very easy way to find a basis for W. Namely, just take V, T of V, T squared of V, until you have K vectors. K minus 1V. That's a basis for V. And let me again just hand wavy show you why this is true. So let beta, well, just start with V and then apply T to it. T of V, T squared of V, dot, dot, dot. Well, this process has to stop because at most, n vectors, where n is a dimension of V, this has to stop because then it won't be linearly independent anymore. So write this as Tj minus 1. sort of be the largest linearly independent set you can process with those by applying T. So linearly independent. So J, the biggest one, such that this is linearly independent. Possibly J is 1, which is okay. And let's just show then can show that Z, which is the span of beta, we can show that this is T-invariant. In other words, because if W, how can I say it? Why is it T-invariant? Well, of course, if you apply T to V, you get an element in here. You apply T to this, get an element in here. But what happens if you apply T to this vector? Then Tj of V, remember, we showed that we assume J is the biggest one that makes it linearly independent. In particular, Tj of V, if you consider V up to Tj of V, it's linearly dependent. And because this smaller set is linearly independent, but this bigger one isn't, it means this one, you can write this as a linear combo of these other ones. So Tj of V is in the span of V, T of V, up to Tj minus 1 of V. And that's precisely Z. So you see, if you, basically, you can use this fact that if you start with a vector in Z, so a linear combo of those vectors, and you apply T to it, then T of that vector is still in Z. So in other words, if W is in Z, then T of W is in Z, and in particular, what that means is that, remember, we have this T-cyclic subspace. The T-cyclic subspace is the smallest invariant subspace that contains V. In particular, because W is the smallest one, W is included in Z. So by smallest, W is included in Z. So W is smallest. But on the other hand, look, Z is the span of those vectors. So which are particular vectors, more particular than this one. So this set, this span is smaller than the span of the bigger space. So we also get that Z is less than or equal to W. So Z equals W. And in particular, what does that mean? The dimension of W is the dimension of Z, but by definition, this is a basis for Z, and this has J elements. So dimension of W, dimension of Z, which is dimension of W, which is K, and dimension of Z is J. So J equals to K, which tells us that this set is with K minus 1 is linearly independent, and we've just shown it spans W, and therefore it's a basis. So it turns out if you know the dimension of your cyclic subspace, it's very easy to generate a basis for it. All right, that was the first part. The second part is even more interesting. Suppose you can show that A0V plus A1TV plus dot 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 plus AK minus 1 TK minus 1V plus TKV equals 0. Which is true because we've shown that, this is a basis. So in other words, Tk of V, you can write this in terms of those vectors. Then actually, it's easy to calculate the characteristic polynomial of the restriction. Then the characteristic polynomial of T restricted to W, it's simply f of T, or did I call this? Let's call it g of T, equals to minus 1 to the k, A0 plus A1T plus dot 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 plus ak minus 1 tk minus 1 plus t to the k. In other words, if you can find a linear dependence relation between those vectors, which you can, then it turns out you can easily find the characteristic polynomial of your restriction, which is the heart of the Cayley-Hamilton theorem. And why is that true? So, remember, this set is a basis for W. So, we can actually find the matrix of T, I guess T restricted to W with respect to this basis. So what you're doing, again, this is the basis for W, so V, T of V, dot, 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 Tk minus 1 of V, and you want to express it in terms of V, T of V, dot, 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 Tk minus 1 of V. Now remember, how to find the matrix of your linear transformation? You apply T to your basis vectors to get TV, T squared V, dot, 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 up to T to the KV. Now, TV, how can you write this in terms of those vectors? Well, 0, 1, 0, bunch of zeros. T squared V, 0, 0, 1, dot, 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 bunch of zeros, up to this step when you have Tk minus 1V. So 0, 0, dot, 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 1, 0. And what about TKV? Well, notice TKV is minus all those things. So minus A0, sorry, there should be a 1 here. Minus A0, minus A1, dot, 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 minus AK minus 1. In particular, what is the characteristic polynomial of T restricted to W is determinant of this minus lambda I. So G of T is the determinant of A minus lambda I, so not a big bar yet, which is the determinant of minus lambda, bunch of zeros, minus A0, 1, minus lambda, bunch of zeros, minus A1, dot, 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 so bunch of ones, and then bunch of minus lambdas, so minus AK minus 2. And then lastly, minus, so lambda, sorry, minus lambda minus AK minus 1. And it turns out this determinant, that's equal to precisely what we want. That's equal to minus 1 to the k, A naught plus A1 lambda plus dot, 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 plus AK minus 1 lambda to the k minus 1 plus lambda k. And the proof of this is very cute. All you do is you expand your determinant along the first row and you do induction. Why induction? Because if you expand along the first row, you get a minus lambda times the determinant of really the same matrix. So minus lambda, 0, dot, 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 0, minus A1, 0, 1, 0, sorry, no, sorry, 1, 0, 0, dot, 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 minus A2, and then just bunch of ones basically. So 1, 1, 1, 1, 1, and then minus lambda minus AK minus 1, and then minus lambda is also everywhere. I think so. So we get minus lambda. Oh, sorry, there should be minus lambda as well. Sorry, I'm doing this Tuesday evening, so sorry if I sound tired, but I'm okay. And notice this is really a determinant of the same form as here. So if you want to use, and again, there's also this other term. So by the induction hypothesis, this is minus lambda times minus 1 to the k is minus 1 to the k minus 1 of a1 plus a2 lambda plus dot 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 plus a k minus 1. So maybe k minus 2 lambda to k minus 2 plus lambda to the k minus 1. And you have to add now this term, so minus a0 times the rest of the determinant, which here is actually not that bad, so that is, because basically all the other terms cancel out, so plus, I think, let's see, minus a0, yeah, no, well, we have an a0, so minus a0, but also, you know, remember we're jumping from plus to minus, so we have minus 1 to the k minus 1. a0 times the determinant of 1 minus lambda, 0, 1, minus lambda, 0, 0, 1, minus lambda, dot, 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 up to 1. And this is a diagonal matrix, so the determinant is 1, and so we get minus minus, so minus 1 to the k of a naught. And then if you put all of those together, you factor out, so we have a minus minus, so minus 1 to the k of, let's see, lambda a1 plus lambda squared a2 plus dot 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 plus ak minus 2. Lambda k minus 2. Does that make sense? Oh, so yeah, a1 is still ak minus 1, I think. Yeah, here, ak minus 1. Yeah, because you're starting with a1 and then you're going up to, yeah, okay. And then what we have, ak minus 1, lambda to k minus 2, plus lambda, except you're multiplying by lambda, so lambda k minus 1, and then plus this a0, sorry, no, plus lambda k plus a0, and then you get minus 1 to the k. Now a0 plus lambda a1 plus lambda squared a2 plus dot 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 plus ak minus 1 lambda k minus 1 plus lambda k. And I hope that's what I wrote. Let's see. Oh, I erased it. But anyway, that is the result. Okay? All right. Now, with those lemmas in hand, we can finally prove the Cayley-Hamilton theorem, and you'll see the hard part is done. We have done most of it, so now the rest is just fun and play. So, proof of the proof of the Cayley-Hamilton theorem. Woo! Of Cayley-Hamilton. So let f of lambda be the characteristic polynomial of f. And what we want to show is that, you know, suppose you have a linear transformation t from v to v, you want to show that f of t is the zero transformation. So the matrix analog is if you have a matrix, f of that matrix equals to the zero matrix. So it's entirely similar. And in other words, what do we want to show? Let v in v in v, then show if you apply ft to v, you get the zero value. Now, this is obvious if v is 0, because ft of 0 is just 0. So assume that v is non-zero. And let W be the T-cyclic subspace generated by V. So in other words, it's the span of V dot T of V up to the dimension, so Tk minus 1 of V, where K is the dimension of W, which is less than N, because it's a W is a subspace of V, so, and that's by lemma 2a. Now, consider the set up to Tk plus 1. WTV dot 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 Tk minus 1 V and then Tk of V. Now, by I think one of those lemmas, I think lemma, was it still lemma 2a? Yes, by the lemma 2a, this we know is a basis for W. And in particular, because you're adding this redundant vector, what this means is that Tk of V is a linear combo of the other previous vectors, which you can write as follows. So what happens now stays between us. Namely, we get a non-trivial linear combination that gives you 0. So A0V plus A1TV plus dot 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 plus AK minus 1 TK minus 1V plus the redundant vector Tk of V equals 0. So this is just another way of writing that Tk is a linear combo of the other vectors because the whole set is linearly dependent. This is linearly dependent, and again for some A0, A1, dot, 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 up to AK minus 1. Okay, in F. All right, in particular, we can use lemma 2b that says, because we have this relationship, we know what the characteristic polynomial of T restricted to W is. It's namely this one. Minus 1 to the k, a naught plus a1 lambda plus dot 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 plus ak minus 1 lambda to the k minus 1 plus lambda to the k is a characteristic polynomial of T restricted to lambda. That's just by definition of W being the T-cyclic subspace, and this is the characteristic polynomial. So, by lemma 1, because this is a characteristic polynomial of the smaller space, we know that Fg divides the characteristic polynomial of T. In other words, f of T equals to our mini polynomial, or I guess let me write it as some polynomial times our mini polynomial. And it turns out that's enough to conclude. Why? Because of the following. Let's calculate ft of v. We are done once we show this is 0. But ft of v, by definition, f is h times g. So it's h of t times g of t applied to v, but that's just h of t times g of t applied to v. But g is this thing, so it's h of t times minus 1 to the k, a naught plus a1 t plus dot 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 plus ak minus 1. T to the k minus 1 plus t to the k applied to v, and lo and behold, we get what we want, and that is h of t minus 1 to the k, and then basically a naught v plus a1 tv plus dot 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 plus ak minus 1. tk minus 1v plus tkv. But what do we know? This expression is precisely 0 by the definition of a 0 up to ak minus 1. So this is the 0 vector. So we get ht times some constant of the 0 vector, but that's ht of 0. And any linear transformation applied to 0 is just 0. So it is 0. So indeed, ft of v is 0, and that's why ft satisfies that it's the 0 polynomial. Zero linear transformation. And I think then just by choosing bases, right, giving a matrix, choose a certain, consider maybe the left multiplication transformation, then if you put bases, brackets on them, then you do get that in general, for any matrix, f of a is the 0 matrix. In other words, the matrix satisfies its characteristic polynomial. All right, I hope you like this Cayley-Hamilton excursion. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.